Hi, welcome to Quantum Mechanics Paper 1 video series, the place where you learn quantum mechanics from scratch. If you have not watched any of my videos yet, I strongly encourage you to watch all of my videos from the beginning. And the prerequisite knowledge is there in my previous videos. And I'm going to put all the links in my description. You can access all the videos via those links. Right, I strongly encourage you to watch. Right, then today, a God equation, one of the God's equation is going to be introduced to you, and this is a well-known Schrödinger equation. So sometimes you might have already seen what Schrödinger's equation is, but I'm going to just prove the Schrödinger's equation from scratch. Why? I have noticed that most of the students know Schrödinger's equation. They know sometimes, they have seen what Schrödinger's equation is. But in the first place, why Schrödinger really wanted to construct this equation? Why he really wanted to have a new equation that describes all the quantum systems? There are some limitations, of course, but this is the fundamentally the F equals ma, how important F equals ma in classical physics. Just as that, the Schrödinger's equation is important in quantum mechanics. So, for example, if you really want to, if you don't know anything about the wave function, so you really want to construct a wave function, you have to use Schrödinger's equation. There are some limitations of Schrödinger's equation, yes, indeed, but this is a very powerful tool. Just as you apply F equals ma in classical physics, Newton's second law. Right. So let me start from the scratch. Now, all you have to understand is, guys, the Schrödinger really wanted, and he was inspired by two things. Number one was the Heisenberg's matrix mechanics, right? So the mechanics itself is a very deep concept. I'm supposed to talk about mechanics into the depth later in another video series, guys. But here simply he was inspired by number one is de Broglie's equation. We already know that here in my previous video I showed you that particles can behave, or simply particles are not really particles unless we observe, right? So this is the very first inspiration, right? This is what you really need to understand in the first place, right? So what I really want to point out is, if any sort of particle is behaving as a wave, right, you should be able to describe this system using fundamental physical quantities like momentum, like energy, right? So in mechanics we have another branch, right? Number one was Newton's branch, number two is the Lagrangian branch, number three is the Hamiltonian branch, right? And we already know that the Hamiltonian represents the total energy of a system. For example, H is the total energy, kinetic energy plus potential energy. Let me take it as T plus V for simplicity, right? But we already know that these are not continuous functions when it comes to quantum systems, guys. When it comes to quantum systems, we have to use operator mechanics or operators to define these functions. This is the catch. This is the very first point where you have to improve your intuition properly, right? So then he mentioned that even Schrödinger's Schrödinger's main inspiration was, he strongly believed that total energy of the system is, let me take it as E, is equal to kinetic energy plus potential energy according to the conservation of energy, right? P or V, as you wish. Either you can put V here, right? But now we already know that we have to somehow relate these things to wave function, right? Because wave function is the heart of the particle, which defines every single thing about the particle when it is not observed. So it is when it really appears as a wave function, right? Let me find some more space. Right. Now, we already know that even in last video, I introduced to you that this one, the wave function, can be properly uh, expressed as e to the power I kx minus omega t. You might be wondering what this a is. So how did it show up? Out of nowhere? No, not actually out of nowhere. This is a very important term, guys. It will play a very important role later on. This is called the normalizing constant. But yeah, so if you are not pretty familiar with this one, it doesn't matter. Just completely forget it for a while. But it's a part of this calculation, and I just take this as a part of this wave function. But what I told you was, uh, yeah. So no matter what, as this is a solution for classical wave equation, and in the meantime the quantum system should be properly explained by this one. Yes, both of those things are satisfied by this wave equation, so that's why we went ahead with this one, right? So, and the next important thing is, guys, the quantum physics is not like classical physics. We already know that, yeah. So if you view it through the classical lens, this one, this, yeah, k can be written as p squared in terms of momentum plus potential. We already know that p squared over 2m represents the kinetic energy, plus this is the this is the potential or potential energy. But here in quantum mechanics, guys, energy is not continuous, and even momentum is not continuous. So when you dive deeper and deeper into classical physics, you will realize that classical physics is not strong enough to describe these things. So in Heisenberg's um, operator mechanics, he introduced some terms. So I'm not going to discuss those things, as that's not a part of my this video. But anyway, uh, we choose operators. Can you remember in my last video I introduced what exactly quantum operators are, right? So what quantum operators usually do is, if you for example, let me take momentum operator, and if you place momentum operator in front of this phi, simply if you apply momentum operator to the wave function, actually that's the same wave function, but I put a pet name here because it's a nickname, as this is a bit complicated to write all the time, 5xt. I simplified that and wrote it as phi. But anyway, you should end up with the value of the momentum itself times the wave function itself again, right? So my point here is, uh, anyway, if this is, now this is a very good eigenfunction, guys. I told you there are some specific selected functions in quantum mechanics that we choose as eigenfunctions, but not every wave function is an eigenfunction. It doesn't matter. Later on we will and I will walk you through non-eigenwave functions, and we will be able to deal with those things with current understanding and current knowledge, right? But what I want to really emphasize here is, so this one represents the value of the momentum itself. So this is, it's not the classical picture, guys. This is completely different. This is not the classical picture anymore. This is how you uh, picture, or how you portray the quantum picture to see those physical quantities, momentum, energy, no matter what. For example, the energy, the corresponding operator is Hamiltonian operator, not there's no specific energy operator, but we use Hamiltonian. So, but if you put Hamiltonian in front of this wave function, you will end up with the energy of that eigenstate times 5, right? So don't worry about eigenstates yet, guys. So my entire next video will be dedicated for these eigenfunctions and eigen solutions and eigenvectors and eigenvalues. All of those things will be introduced in my next video. But anyway, what I want to here emphasize in this video is uh, so if you place an operator, if you if you just insert an operator like this, you will end up with the value of this function, right, which is p here in this scenario, right? So now Schrodinger's challenge is he really wanted to replace his equation, this one, with operators, right? So instead of e, now he has to write the corresponding operator, and we already know that corresponding operator is Hamiltonian, right? So now here Hamiltonian operator of phi is equal to here p squared operator over 2m plus v, and then again wave function, right? So throughout my entire video, guys, I'm going to show you that we can find a very good mathematically intuitive operator for this one and for this one, and I'm going to construct the game changer, the God equation. What is it? The Schrodinger's equation, right? So listen to me very carefully. Now, yeah, it's like playing chess. Sometimes you make a random move, right? And then sometimes you see the big picture later, right? It's like playing chess sometimes. So all you have to do is now, not you actually, but Schrödinger did was, he was finding for something that describes the momentum operator, right? So what he did was, all of a sudden he decided to get and see uh, the first derivative of x. This is called the spatial derivative. So what he did was he got the spatial derivative of this wave function. So even let me do the same, right? I have no clue yet, but let me work it out and see what we will end up with, right? So now I'm going to put the spatial derivative, very first one. So phi xt and x. Let me see what I end up with, and even here normalizing constant, and here I kx minus omega t, and here again x, right? So now I can clearly see that for simplicity I'm going to write it like this hereafter. Let me keep it as it is, right? And then here a is a constant anyway, and here omega t turns out a constant, as here it is it is a t, here we consider delta x, so that t would be treated as a constant here, so that we'll end up with I here and here k, and now exponential again I kx minus omega t, right? Now you can clearly see that this one and this one, when you combine these two parts together, that is exactly the wave function again, right? It's the wave function itself. So I can finally end up with x is equal to the wave function, or you can say I k wave function. Yeah, so you might sometimes you might disagree with me. This is not a ik, doesn't make any sense. It's not actually momentum. So what is the use of this? You might be wondering. Let me hold on for a while. I'm going to show you. Now, though we ended up with something like this, right? What if I do something like this? Take a look at this, guys. Now we have this uh, above 5, my wave function over kappa x is equal to I k 5. This is even imaginary. Doesn't make any sense. But what if I multiply this one by minus, then uh, as I really want to have the momentum here, but we already know that there's a relationship between momentum and yeah, P is equal to h bar k, if you remember this one. Even in my last video, I introduced this to you. So it came from this actually. So P is equal to here Derive equation lambda, sorry, h over lambda. We can use this one. So then I simply turn it into this relationship, and this is wave number. So if you have not watched this one, because I have to save my time here to introduce for my today's lesson, I have to deliver my today's lesson, guys. So I'm going to put down the uh, link. You can access that video, go through that and watch the video if you want. But so I want to, yeah, this is what I want to construct here, guys. What I'm going to do is now I'm going to just multiply this one by minus I and h bar, right? So now I will end up with this relationship, minus I and h bar times again here I and phi. Oh, my bad, k is also a part of this one, k is there, and phi, right? Now we are about to get something meaningful now. So now here minus I, here h bar, here phi, yeah, about x is equal to, let me use something else, a different color. So now here I times I is I squared. We already know that I is minus 1 square root, so that I squared is minus 1 again. So minus 1 times minus 1, it's 1. And here we will end up with h bar k phi, right? This is a profound relationship, as a magnificent relationship, guys, as here we can clearly see that this is the momentum, right? So wow, very interesting. So now I have already ended up with p phi. So now I can recognize this as now here phi, and I can recognize this as the momentum operator, and here this is my pi, and here h bar, and this is actually momentum times this is pi. So now I have just recognized what the momentum operator look like. So it's p momentum operator is equal to minus I, and here h bar, here dabba over dabba x, right? Good. Right now, yep, this is what the momentum operator look like. So what I'm going to do is now I'm going to just follow the same sort of approach and find out what the energy operator look like, right? Yeah, let me move on to the other page, the other board, as I need more space. And yeah, let me work it out. Okay, now the Hamiltonian, which is the corresponding energy operator, right? Again, my same wave function, but I want to get something about energy. But this time, again, a bold decision, a bold move. All of a sudden, not me, right? So imagine now Schrödinger's brain is there in my mind. So Schrödinger all of a sudden decided to get the time derivative, first time derivative of the wave function. So let me do the same. Let me follow what Schrödinger did was, right? So then I'm going to follow the Schrödinger's approach. So then I'm going to put da bar here again a, and here this time it's the time derivative kx minus omega t, right, over, oh sorry, and over here da bar x, sorry, da bar t this time. So what I did was I'm going to get the time derivative of wave function, right? So now we will end up with now here k is a constant, x is a constant, as t is the variable here. So now it will be a, yes, still it's the constant, and here I comes out of the constant, and then it's omega here. So kx is completely, it's a constant, so that will end up with here, but be careful, this is minus, so minus comes out of the bracket, and minus will join with this constant, and then it's finally here again e to the power I, here kx minus omega t, right? But you can clearly see that again this one and this one, when you combine them together, it is the wave function itself. When you combine them together, we'll end up with the wave function. So now again I can clearly see when I get the time derivative, first time derivative, we'll end up with minus a here, and here I omega, and here again, oh my bad, a slight mistake here, then here we'll end up with here I omega, and this one and that one, it's the wave function itself, right? Okay, but again, it doesn't make any sense, there's no relationship, so it doesn't actually directly help us to find out anything, but we have to be smart. It's like a chess game, as I mentioned previously. So though we ended up with something meaningless, we already know that energy is equal to h bar f, sorry, h bar omega. Even I derived this one previously in my previous video. If someone is confused by saying this is not a coincidence, or this is not coming out of nowhere, it's a relationship that we mostly use in quantum mechanics, even in classical physics, quantum physics, everywhere this equation mostly shows up, so it's not a new thing anywhere, right? So it appears everywhere. So all you have to understand is here, if you end up with h bar and omega, it is exactly the energy. So what if I try to construct this one again, right? I'm going to construct this again. So in order to construct this one, I need to have this I, and I have to deal with this minus and this I. So what I'm going to do is, right, so what I'm going to do is I'm going to get here I'm going to get the product of here I times h bar, right, I times h bar here, come on, right? So now it's minus I times again here I, and here we have h bar, and here phi, right? Okay, okay, good. Let's go ahead. I need some space. Let's move on to, let's flip the boards and start to take down the notes on the other board, right? So now right, I keep my momentum operator as it's useful. I keep my momentum operator as it is, but we have just found out, right? Then I'm going to deal with the energy operator, right? So now yeah, I h bar here, and here da bar phi over da bar t is now equal to here yeah, minus I squared, and here h bar omega. Yes, I think even here I should put omega, and here omega, and here phi, right? So then here I h bar da bar phi over da bar t is equal to here minus I squared. Sorry, I squared is minus 1. Minus 1 times minus is plus 1. So we will end up with something familiar. That this is not a new term. This is exactly the energy, guys. Right? So now I have just found out what the Hamiltonian operator is. So now I can clearly see that this one is I h bar W over W t and times phi is equal to here its energy times phi. Right? So now I can clearly see that this is what the Hamiltonian operator is. Right? So now my Hamiltonian operator is equal to I h bar W over W t. Right. We are on the verge of getting something meaningful. Right. Okay, guys. What I'm going to do is now, let me substitute these things to our operator relationships, guys. So what we have just derived. Yeah. So I have derived something for the Hamiltonian, and which is energy, and the momentum, right? So now we know what these operators look like, right? So then I have to deal with this one now, and these are no longer continuous functions, those are operators, right? Let me handle these operators now, right? So now, as I mentioned previously, if you really want to get something from this one, so we have to write them like this, right? Then energy operator times the wave, the function here xt should be equal to momentum operator over 2m plus, this is actually Vx, so V simply the potential energy of that one, and here the wave function, right? So let me put the values, let me put what we have already found out to this equation, right? So then we already know that Hamiltonian operator is, that we have already found out what the Hamiltonian operator is, which is I h bar W over, and here W phi over W t, that's the time derivative, is equal to here, actually momentum operator is here minus I h bar, and here W over W x, which is the spatial derivative, squared over 2m plus here V, right, times the wave function itself, right? Now we have yeah, so I can keep these as is. Now I h bar here W phi over W t is equal to, now when I get the square of this one, minus squared is plus, but I squared is again minus 1, so then plus times minus, it will turn into minus, and here h bar squared over 2m, but don't forget that here this is W squared now over W x squared, right? And plus potential, and now the phi is waiting over there until he meets these two terms, right? We are on the verge of getting this profound equation, guys. So let me shape the last bit of this one. Hold on, right? So now we have almost derived this profound, this magnificent equation, guys. What is it? I h bar W phi over W t is equal to here minus h bar over 2m here W squared, here phi over W x squared plus V phi is what we recognize as the most important, the majestic and profound Schrödinger's equation, right? But Schrodinger's equation, yes, though it solves so many problems in quantum mechanics, though it helps you a lot to deal with quantum mechanics, even it itself has some limitations that you can't avoid. Number one is, guys, the collapse. Now, the Schrodinger's equation is simply a unitary one. So, according to Schrodinger's equation, the wave function is unitary. The collapse is not unitary, guys. Collapse is not unitary. We already know that all of a sudden, when you observe, as soon as you observe, or as soon as you measure, as soon as you detect this quantum particle, you get, all of a sudden, you get, or it collapses, the wave function collapses, and you get a weird answer, right? So, why does it happen? Believe me or not, this will lead to another paradoxical um, philosophical uh, philosophical debate. So yes, that's a problem. So then smoothly this one explains the transformation of wave function and how wave function transform from one point to another. But the problem with the Schrodinger's equation is still the Schrodinger's equation cannot alone solve the collapse problem, right? So there are some modifications, Copenhagen interpretation, many world interpretation, so many interpretations of the cubism, and we can discuss about those interpretations later on. Uh, those are a bit deep concepts, but anyway, uh, those are very deep stuff. Entanglement, and even entanglement is mysterious. Here we need to have decoherence and um measurement decoherence concepts we need to use, right, in addition to or apart from Schrodinger's equation. Schrodinger's equation cannot solve those problems alone, right? And the other important thing is relativistic scenario with that picture is much more deeper than uh, the simple systems, guys. This is applicable for simple systems, but as soon as relativity enters, uh, the Schrodinger's equation is insufficient. It's incapable of solving issues, right? So there are some limitations, but this is a milestone, guys, as Schrodinger's equation can do a lot of things alone that no one can else do, right? So in my next video, I'm going to walk you through uh, 1D potential walls, and that's a very good starting point where you can start to see quantum nature, quantum picture, and then I'm going to walk you through free particle later on. Even though free particle is a very simple concept, I mean the simplest form of a particle, even it will lead to the quantum nature of that will lead to, or it will corner us mostly, and we have to deal with some complex complications later on. But I'm pretty sure you'll be able to figure out things with me, and you can drop your questions anytime. Feel free to reach out to me, right? Yeah, thank you for hanging out throughout the entire video, right? See you with the next episode.